Fine. So this is the last but not least group, the machine translation group. Translation in an hour is what we're going to get, right? On any language, anytime, anywhere.
I think we have an hour and a half. Okay.
Well, I don't know.
You'd stop me for when I talk too long. All right. Can you hear me okay? Okay. So I'm going to talk about the statistical machine translation workshop. In this workshop, we decided to tackle a pretty big, ambitious problem. It's hard to get good translations. It's hard to quantify when you have good translations. It's a big engineering enterprise. So fortunately, we have a really good team, and this is quite a good experience, a really nice experience, and to work with such good people and have such a focused goal. I really support this workshop. It really is something unique and great. Okay, so I'll start with ancient history. So Warren Weaver had some idea that struck him after World War II, and he wrote some really forward-looking articles, interesting articles. He said, when I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode. So he's an optimist. He said, let's take some techniques that have worked well after the war in cryptography and apply them over to this other area and see if we can have some success there. So he's optimistic. Now, this has gotten a lot of currency in computational linguistics, this particular quote. Most people don't know that he wrote this in a letter to Warren Weaver, who responded immediately, that is, a month later, right? As to the problem of mechanical translation, I frankly am afraid the boundaries of words in different languages are too vague to make any quasi-mechanical translation scheme very hopeful. So this situation is just continuing today. We have optimists and pessimists both with respect to whether this is a useful point of view for attacking the translation problem, and whether translation is getting significant improvements in translation quality is a feasible goal. So we're trying to do experiments to help resolve this debate. Okay, so bringing it more up to date, IBM had a very interesting project in the late 80s, early 90s called Candide. So they took the Canadian parliamentary proceedings and as a kind of Rosetta Stone, French and English. They aligned up the sentences, stored sentence translations, and induced probabilistic translation rules from those stored sentence pairs to translate, and use those rules to translate novel sentences. This was a really new approach, and they wrote it up in, most of it up in these kinds of reports. So the interesting thing about this was that you could get a lot of linguistic knowledge acquisition done completely automatically. And in contrast to some of the other approaches where you had to add each linguistic piece of information very carefully by hand, one at a time. Another interesting thing was they were ultimately able to equal and slightly exceed commercial level machine translation quality. Even though the commercial systems had a great deal of manual work and decades of work behind them. And I guess the third interesting thing is that it looks like there's a lot of opportunities for improvements by changing the statistical model. So I'll try to give you an idea about, in the next few slides, about how the thing works, just for background before I get on the workshop goals. So here's an oversimplified view. You see some of the simplest possible statistical machine translation system you could build. You see some French sentence out in the world, you put all the French words in a bag, you shake it up, you send it off to the translation model factory. Okay, this factory sends you back a bag of English words. You send this bag off to a language model factory, and this sends you back those words arranged in a nice, hopefully grammatical, fluent order. And again, the interesting thing is these factories can be built automatically from online text resources, particularly parallel text. Okay, so to get just a little bit more detailed, given a French sentence F, we imagine that any English sentence E is a possible translation, but some E's are more likely than others. So we want to find the E that maximizes this probability here. And that's the same as finding the E that maximizes the product of these two factors. And this, again, is the language model factory and the translation model factory. Okay, their job is to assign these probabilities to pairs of strings or individual strings. And a kind of nice thing about this is that these factories can be actually weak and not particularly great themselves, but when they come together, there's a nice synergy. So, for example, consider if you had these following English translations to choose from for some French sentence, say. Well, we can make a check mark by all the ones that seem like reasonable English, grammatical English, say. And we can make a check mark by the ones that seem to contain translations of the words that we saw in the original French sentence. Right? So individually, oh, sorry. You want to see the formula while we're at it? Okay.
No, at the back, they're too far up to see the top.
The ceiling cuts off the top of the projection.
I got you. Thank you. Something like that. All right. Okay, so that's the first joke. We got that over. So these, individually, these factories.
Now you are covering
All
up.
right, all right.
Just go back.
I gotta keep going here. So obviously not everyone is satisfied with any configuration. All right, so individually these guys can't decide on what the best translation is. They're both quite faulty, but if you look at where their intersection is, it's much more likely that you hit on an area where the good translations might be. Okay, so now just to go a little bit deeper, let's go to look at actual IBM, one of the models. They built 5 models called IBM Model 1, 2, 3, 4, and 5. And one of the ones that's easier to explain is IBM Model 3. So again, the translation model factory, its job is, given this English sentence and this French sentence, what's the chance that a translator would produce this if they saw that? Okay. So how do I assign that number? Well, you need some theory about how you get from here to there. And IBM Model 3 is an incredibly funny theory, simple theory, that looks like this. It's a 4-stage string rewriting process, where each of these 4 stages are different, and you start with English and you wind up with non-English. In the first stage, you decide a fertility of every word. So that means how many words will this English word ultimately produce in the foreign language. So did maybe produces nothing here, and not produces 1 word, and slap will produce 3 words. So you make this decision for each word. Next, you decide after each of these words, do you insert a null token? And these null tokens are going to be responsible for generating function words in the foreign language that don't have equivalents in the English language. The next stage is a single one-for-one straight substitution of words for words, where you substitute, for example, bruja for which. And the final stage is a permutation of these words to try to get them into a better order. Okay, so it's an incredibly naive, simple theory that, the redeeming feature is that you can explain pairs of sentences using this theory. But it's certainly gotten very simple from a linguistic point of view. And yeah. Okay, so how do you get the probability of this sentence being produced by this one? Basically, roughly, it's the product of all these red arrows, numbers associated with these red arrows. So what's the probability that did would have a 0 fertility, for example? Or that green would be translated by verde in text? And these are stored, these numbers, you can actually, for any one of these arrows, you just go to a table, 2-dimensional table, and look it up. So this is an in table, so you can look up what's the probability of a fertility 0 given the word did. So these models are just 2-dimensional tables of floating point numbers. Okay, so how can you learn these from bilingual text? Well, if you had text that looked like this, you'd be in really great shape, because if someone had hand-aligned all these things, if you wanted to know what the probability of thee translating as this or that or whatever, you just go observe thee in your parallel corpus and just see how people have translated it and get that number. So maybe it translates as la 20% of the time. Unfortunately, our bilingual texts, like you get from Canada, look more like this, where you don't know these mappings. But fortunately, you can use bootstrapping to make a good guess at those mappings completely automatically. You start out with the fact that these seem to co-occur a lot, so you start hooking them up, and that influences other decisions that you make. And this was the central contribution of the IBM Candide effort. Now, it sounds like a simple idea, and it's pretty simple, but pulling it off in practice is a whole other story. There's a lot of complications. If you start out in a bad part of the space when you do the bootstrapping, you can wind up with a lousy solution. So you need to start out in a good part of the space. That's why this is Model 3. Model 1 and 2, their job is sort of to get you in the right part of the space before you do this bootstrapping. Another problem is that there's too many alignments to consider when you're trying to, too many of these word connection alignments to consider when you're doing the bootstrapping. So again, you have to make some compromises and come up with some intelligent strategies for dealing with those problems. Okay, so where did this IBM project go? Well, most of the people involved went to Wall Street to predict future stock market movements instead of sort of what's the next translation or what's the fertility of a given word. And since then, there hasn't been a really large-scale duplication of this effort. So, and the technology is certainly not used in machine translation in practice. So it's very different from speech, right, where this sort of idea caught on in the 70s and didn't work well then, didn't work that great in the late 70s, didn't actually work that great in the 80s, but eventually you've got products that you can use. So for example, I use a dictation engine every day, and I couldn't do that 5 years ago even. Okay, so it seems like the results now, just like in speech back in the 70s, are not significantly, well, okay, leave that. So the results are not significantly better than handcrafting, in machine translation anyway. There's also this big data bottleneck. You got to have a lot of parallel text. The IBM papers, I'm sorry to say, are extremely dense and take years to understand. The decoding, the actual translation process was very slow. It could take up to it could take up to a month to translate, I think, 100 newspaper articles, right back when evaluations were held a few years ago. No user customization like you typically get from a machine translation company. And I think one of the more important things is no distributed code to spur experimentation. So people have been wanting to get into this field because it looks like a very promising path, lots of experiments waiting to be done, just like all the experiments that have been done in speech over the last 20 years. In machine translation, they haven't been done yet, and nobody knows which ones are going to work and which ones aren't. But it's hard to do those experiments because for example, all the IBM code just basically went away. And so there's a lot of research groups who are getting into this and redoing efforts or inventing new methods, but no one's sort of taken up where those guys left off for those reasons. Okay, so our goals in the workshop were to try to jumpstart stuff a little bit more by providing an MT toolkit based on the IBM Candide work for distribution. So we decided to do a Model 3 learning training on bilingual text and to do a decoder that would produce translations. And these are both very substantial software projects. So our aim for this toolkit was two types of users. One is a guy who says, I have a parallel corpus, I don't know what to do with it. Well, come and try this thing and see what you get. Another one is someone who has an idea in statistical machine, thinks it might apply to statistical machine translation, wants to show it helps, but right now there's not much you can do. So in speech, for example, you can get the HTK toolkit or some other toolkit, run your idea on top of that and show improvement. It's impossible to do that in machine translation. So this is our major goal. Another goal is to try to do a Czech English statistical machine translation system, because here you're talking about more distant languages than IBM dealt with, a rich morphology, a relatively small parallel corpus. We also wanted to provide some learning curves, and this is something else that hasn't really been done in statistical machine translation very much. Things like, what is the effect of corpus size on MT quality? All right, so should we go out and get another 1 million pairs of sentences? Is that going to help, or should we broaden it, or should we commission more translations, or nobody really knows. Also looking at like machine internal measures against corpus size and so on. So we wanted to produce some of these. We wanted to look at improving on Model 3 by looking at new models of word reordering. And then we also wanted to do a surprise, which was, I can now reveal the surprise, which is to do a machine translation in a single day for a new language pair. So we decided we scheduled for last Friday, just get together, take the tools we have, get a new language, shove it through all the pieces and see if we could get it to work. Okay, and we picked Chinese English for that. Okay, so this is actually the original workshop goal slide from 6 weeks ago. So you can judge sort of for yourself if we were successful or not on this on these things. Okay. Any questions so far? Okay. All right. So here's a picture of the Candide system. They had model 1, 2, 3, 4, and 5 translation models, which would extract more and more knowledge out of parallel text. They had a decoder. They had morphology. Online dictionaries were integrated. And context-dependent translation, so words would translate differently depending on where their neighbors. And all that together made up the kind of Candide at its height. And that system was one that was able to slightly outperform commercial systems. So this is where it was going in. They considered that there were many other ideas to improve further these results. Our goal was more modest. It was to build a toolkit that we call Egypt now, which would include these 3 models and a decoder. And this was already a very substantial project, so we would have been happy if we were successful in building a toolkit that had this. As it turns out, we did a little bit more. You'll see we did a little bit of morphology on the non-English side. We did a version of Model 4, and we did a fair amount of work on building in online dictionaries. So it was great to have time to do these experiments on top of trying to build this toolkit. So you hear about those. We also had some unanticipated developments. So the undergraduates on our project, Mike Yar and Noah Smith, built a alignment browser to look at these word alignments just so we could easily flip through them and see if how our system was doing in its training, and they call this Cairo. And they'll give a demo of it right after I'm finished talking here. Also, this was not unanticipated, but I want to put this on the slide because it's kind of surprising. I mean, the corpus preparation turned out to be very hard part of this. And two of us, Dan Malavid and Jan Sujin, spent full time organizing the corpora, doing tokenizers, dividing into training and testing, and also Mike Yar built a tool for doing this too. And a lot of this is language-specific knowledge. So without this kind of manpower on that side, there's no way to pull this off. It's not just a bunch of training algorithms. Okay. Also, we unanticipated. We found new Hansard text, and these are the Canadian Parliament from the last 3 years. David and Yureski and Dan Malavid ran onto a great homepage where they said it may be used without seeking the permission of the Speaker of the House of Commons, so that means we can distribute this, right, or pointers to it, with our toolkit, provided it is accurately reproduced and does not offend the dignity of the House of Commons. So if you've read these debates, this is questionable, and especially if you read our translations, it's questionable. But I think it should be okay. And if we can distribute the, alignments and very large corpora to researchers, then that overcomes another bottleneck that people have when they want to get into this. We were also able to achieve large speedups in bilingual text training for Model 3, and Franz is going to talk about that. This made a huge difference in the amount of experimentation we were able to do. We thought we were just going to be able to do a couple of experiments during the workshop, and it turned out we were able to do many every day, and try to discard bad ideas and get new ideas. And based on what we had read about in the IBM papers and our initial implementation, this was looking very hard. The decoder, also the IBM decoder, running it, I guess, was like watching the grass grow. It was incredibly slow. Our decoder that John Lafferty built is not like watching the grass grow. It actually runs very fast. It was a big surprise. And he'll be talking about the decoder. Also, both of these things were very large software projects. Maybe we'll get an idea of how many lines of code, but a huge part of the workshop, for better or for worse, is spent debugging these things to make them work. So it's a tremendous amount of work. And then we also produced an in-depth tutorial on, partly for the students involved in this project, so that everyone will be ready and up to speed before we started, but also for anyone else who wants to start completely from scratch and learn all the details of this sort of model. Okay, so I'll spend a few more minutes now talking about the kind of learning curves that we wanted to build, and then I'll turn it over and we'll hear about all these other things. So one of the things we wanted to know was, for example, how does corpus size relate to human quality judgments? We also wanted to look at things like how does corpus size relate to perplexity, which is a more system internal objective measure of how much knowledge is being sucked out of the bilingual training corpus. We wanted to look at perplexity versus human judgments. We wanted to look at things improving as the learning iterations increase. And we got reasonably far on this. We got a lot of interesting learning curves. We didn't get as far as we wanted to. Basically, we hooked up the decoder to the learning system last Friday, and we were able to get translations now, but big evaluation runs with lots of human judgments we couldn't do, but you will see some of that today. Okay, so what I'll talk about in these learning curves that I'm going to show you are mostly related to the system internal measure of how much it's learning. And this is called perplexity or cross entropy. So let me do a slide on this. I recently understood this concept myself, and it's turned out to be not so complicated. So here's how I think of it. I have some English sentence E, and I show it to you. I take some French sentence F, and I put it in my pocket, where you can't see it. And now I give you $100. And you can bet on French sentences all you want that you think might be in my pocket. Okay, you can bet all your money on one sentence. That's probably not a good idea. You might want to spread it out a little bit more thinly. And then I reveal the translation. You show me your bets, and then this is the payoff table. So if you bet $1,000,000 on the sentence that was in my pocket, you break even. If you bet more, you're going to win. If you bet less, you're going to lose. Okay, so you can imagine that a system that could do this would probably could be turned into a good translator, right? Not the other way around. You could be a great human translator and be terrible at playing this game, right? So what this is kind of a measure. Another way to think about it is a measure of whether you can recognize whether two sentences are translations of each other. Okay? And I think it's nice. I mean, any theory of translation ought to be at some point be able to tell you whether two sentences are translations of each other or whether they're just totally unrelated or whatnot. And this could have other uses, like telling whether a text was parallel or starting to give an initial idea of whether a student's translation is just completely off the mark or not. Okay, so what we were able to do is measure, and this was something that the IBM group didn't really measure very much at all, as far as I know, was test cross-entropy or test perplexity. That means these are sentences that you've never seen before. Ask the system, do you think they're translations of each other? If it says they are and they are, that's good. You get a good perplexity. If it says if they're not and it says they're not, that's also good. Okay, so the lower the perplexity, the better. And you can see as increase the training corpus size, this is the kind of relation you get with the perplexity. So you can see at 50,000 sentence pairs, what it's learning is not that applicable to the test set, right? It doesn't recognize these test set things as being translations. This falls off very fast, but still continues to improve way out to here. So. Okay, so perplexity is one way of looking at training. Another way is to actually inspect the alignments, which we did a lot using this tool, which you'll see. So for example, if you train on 50,000 sentence pairs of French and English, you get a phrase like market their grain. It doesn't quite translate right to these or align right to this phrase in French, right? Grain's picking up all these three French words, and market gets 0 fertility. We just haven't seen enough data. But after you give it 500,000 sentence pairs, then yeah, you're doing really well. It's translating these words, aligning them correctly, which means if it sees them, it has a good chance of translating them correctly. Okay, so that's looking at perplexity, looking at alignments, and then you want to look at translations too. So like I said, we just hooked up this system recently and ran a bunch of tests, but we haven't had time to do a lot of evaluation. So, so this is a typical machine translation evaluation. We have one a commercial system, and then our system as it's trained on increasing amounts of text. And so you get a lot of, typical machine translation output. So this systrans says, one mentions no other source allowing to identify the object of this credit. And we say, I refer to any other source allowing to identify the purpose of it. And it's kind of word salad. Other times, it's working out much better. So they say, I do not want to be delayed with the nightmares of the past. And we say, at first, I do not want me contradiction to the end of the past. As we see more data, ultimately we say, I do not want to dwell on the nightmare of the past. So you can see that more data, better perplexity is improving the translations as well. Okay, so now I want to show a different kind of learning curve. And actually, you might see a few of these from the subsequent speakers. So, so stop me if I'm not making sense. So this is a curve that's relating perplexity, which is, again, how much the system has learned from the bilingual text that's applicable to new sentences that it's never seen before, how well it recognizes new sentences as being translations of each other, with a fixed amount of training data. And here we're plotting the learning as it runs in process, so the iterations of the EM algorithm. So this is the models 1, 2, and 3 that we run. And we see that as the thing learns that, yeah, indeed, the test training perplexity goes down. There's a slight jump here, and then it goes down again. And the test perplexity also goes down, so you can see it's learning more as it goes to the right.
Kevin, is there a simple definition of this perplexity?
Yeah, you take the whole corpus, the French side and the English side. You mean like math, right? So what's the probability of the whole French side being a translation of the whole English side? Okay, so that's a product of this French sentence being a translation of this English sentence, blah, blah, blah. And then you multiply all this together and you can get a good huge P of F given E. And then you take the log of that, so that that's why it's better to do lower is better now instead of higher, which would be better in probability. So that's basically it. And that's cross entropy. It's just so that the numbers, well, you guys know better than me, but it looks like so the numbers will be like 40 and 50 instead of 10 to the minus bazillion. Excuse me?
Let's say, I might have missed the point, but when you say this English sentence is very likely to be the French sentence given, when you get that judgment, is it the machine which does the judgment?
Yeah, the machine. So this is a completely automatic measure of this perplexity.
And one last question. And that last slide you had up there, I interpret that as saying that once you went ahead to Model 3, you actually never broke the complexity that you'd achieved with Model 2?
Well, I'll tell you, Phil. I'm glad you asked that question, because this gives me a chance to do animation on my slide like the previous guys this morning did. Of course, the animation is slightly different, but okay, so it turns out that Model 3 is technically deficient, which means we take a phrase like blue house in our translation model, Model 3's translation model, maybe a quarter of the time translates this to maison bleu, a quarter of the time translates this to bleu maison, and a quarter of the time actually translates this to bleu maison. It doesn't put anything here, and another quarter of the time it translates this maybe to maison bleu. Okay, and so it's spending a lot of its probability on things that are not actually strings by piling up words on top of each other. And so they call this deficiency, and IBM people sometimes refer to producing this sort of thing in the translation model as this moral deficiency, okay? Because you're producing things that are not French, even, at least they're strings. Okay, so this is just a technical point, and it can be removed in Model 5, and then you can really do a nice comparison. So, but it's hard, so what we do is look at the alignments from Model 3 and 2, and translations, so you have to do that. Yeah, I mean, if we actually observed a sentence where people piled up words on each other, we could actually translate it and decode it, so if you want to look at the bright side. Okay. Obviously, you're not impressed with that idea. Okay, so we also get a lot of good experience with the fact that non-literal translations often don't have good alignments, which is a reasonable thing to have, to predict. But it's really interesting to get in there and muck around with these things. So in English, it says, "I deny that the sentence is true. The statement is true." And in French, it says, "What he said is false." Right? And these are lined up. I showed you this last week. So it turns out that the system lined up connected true and faux, right? So obviously these things do occur together fairly frequently. But what it's learning from this sentence is not very useful information that it's going to be able to apply. Okay, if you had a, yeah. Now, I'll talk about that in a second. Yeah. Okay, so now I'm going to kind of, let's see, set up some of the talks that follow. So when we look at the Model 3 alignments, there's a lot of mismatches between the way the system is lining the words up and what it's learning from that, and the way we would line things up if we could. So for one, we don't get into one alignment. So 2 English words can't produce a single French word in this model. Okay, it's a problem with the model. One English word has to have a 0 fertility, the other word gets to take responsibility. We also found a lot of this kind of long-range individual movement. So this les in French would move way over here to account for this English the, and this one would move way over there, and it's kind of crazy because you think this whole phrase ought to translate together. Also, rare words tend to collect garbage. That's a feature of the model, a bug in the model. Okay, now when we started to look at Czech, it's just much more challenging, partly because of these curves that I've been showing you, where the smaller corpus, it's hard to extract a lot of data out of that. It's less homogeneous. We were using Reader's Digest instead of these parliamentary debates. The sentence alignments we got were very noisy, and we spent a lot of time correcting the sentence alignment using very nice tools. There's a lot more morphological variation and more significant word order differences. Yeah?
50K what? Sentences, documents, words, bytes?
50K sentence pairs.
Sentence pairs.
Yeah. 2 million words total on both sides. Okay, and we get these perplexity curves also for this much smaller training set. It's actually really interesting. So the test perplexity comes down, as you'd expect, as you increase the training set. And as the iterations proceed, the training data is really learning nicely to account for the training data, but the test data is all over the place. And there's a lot of interesting theories that we have about why this is happening and how to correct for it. And a lot of the things we're doing do correct for that and make that better. Okay, one thing we didn't get to, which will be great to do after the workshop, is to establish this connection between MT quality as judged by human and corpus size. We did a little bit of this, we'll hear a little bit, and MT quality versus test perplexity. Okay, so if we can establish a connection here, and it's not clear what the connection is or what this curve looks like at all right now, no one knows. But if there is some kind of connection here, it's nice because that means you could do your experiments on a daily basis, an hourly basis, discard ideas, adopt new ideas, and try things out in order to prove this, which you get immediately and automatically from the tools we built. And then when it comes time to do your human quality evaluation, which you'll do less frequently, maybe every few months or every 6 months or every year, you can hope that you'll be in a good part of the space when the humans sit down to evaluate your translations. Okay, so I think that's all I'm going to say, and I'll turn it over to everybody else. Here's the schedule so that you can see how far we're going. I just did this overview, and now we'll get detailed presentations from everybody, and then we'll take a break. And then we'll combine the follow-on proposals with our undergraduate presentations into discussions after the break.
Okay.
Oh, you want the mic? All right. Mike, you want the mic?
Yeah. Okay, I'm Mike Yauer, and this is Noah Smith. We're both undergraduates, and we're working on this project. What I'm going to do first is just talk very briefly about a corpus preparation tool that I wrote called Whittle. And what this tool was designed to do is basically, its primary objective was to separate the corpus into training and test sets. And it offers users extensive control over what kind of tests, over the size of the training and test set, and also what part of the corpus the training and the test set was taken from. And because these are things that it is likely that people will want to vary in order to run various experiments. And it is also very important that training and test sets are disjoint over all of the corpora. And so over all runs of Whittle, the corpora will always be disjoint. It also creates vocabulary lists and can replace rare words with unknown, which is another thing that many people have tried to reduce the vocabulary size. And it is written in Perl, so it's very easily portable to other platforms. And it is publicly available and freely distributable, part of the toolkit. And now we'll talk a little bit about Cairo, which is the alignment tool that we wrote.
Okay, I'm Noah Smith of the University of Maryland, and I, with Mike, wrote Cairo this summer. Cairo is a tool for visualization of alignments, currently only visualization. One of the future features that we foresee being added is editing of alignments. Cairo displays an aligned sentence pair with relevant statistics to Model 3, meaning fertilities and distortions, and also the language model. It can show multiple alignments for two sentence pairs at the same time, color-coded. It can display lexical information on foreign words. It has a flexible, customizable interface. And because it's written in Java, it's very easily portable. And you can use it as an application or an applet, so it's very good for use on the web. And lastly, of course, it's publicly available and freely distributed. So we're going to show you Cairo.
Okay, I'll just wait a little bit while this warms up here. Okay, thanks. Can everybody see this okay? More or less, okay. This is the main window of Cairo. You can see that the sentences are aligned on top and on the bottom. The top sentence says il faut vous dire que nous ne sommes pas diplômés, which is a French sentence. And on the bottom you can see two English translations. The top one is one that would be generated by the machine, and the bottom one is a reference translation. So you can. I'm sorry? Oh, read, okay. The top one says, we should say we are undergrads, and the bottom one says, it is necessary to tell you that we are undergrads. And some of you may remember this from yesterday. And so now what you can do is, right here, I don't know if the colors show up very well, but there are actually two separate alignments which are shown simultaneously. One is in red and one is in blue. So words that align in one alignment are aligned in red and the other ones are in blue, and if they're both, they're in purple. So this enables you to see how different translations have different alignments. And by clicking on words, it brings up tables in the bottom. This here is a translation table, which just shows all the various different translations, the most likely ones for the English word say. And this is, over here is the language model probabilities. And there are also distortions and fertility probabilities, and so it's very easy to visualize these things. And we added another feature, which is to display various glosses or other information about each sentence. So here we have, on top of the French sentence, we have a part of speech, and on the very top is a gloss of a simple English word, of a simple English translation. And it is also you can display things in very many different ways. For example, you can display alignments vertically, which enables you to see more, to fit more on the screen. That's basically the essence of it. Also, we wrote very extensive code-level documentation in case people want to customize it to work with other translation systems. So it's all in this format, and it's extremely extensive documentation, so it should be fairly easy for people to extend it. Do you have any questions with this tool? Okay. Now John Lafferty will present the decoder.
Okay. So I'm going to describe a little bit about the decoder. So we called it Decoder Weaver after Warren Weaver, and also because it's sort of the alignments between sentences sort of look like a woven pattern on words. All of these guys were putting nice pictures into their presentations. You'll see them shortly. And so right after lunch, I went out on the web and found this picture. And this is Penelope sitting at the loom, weaving, waiting for Odysseus to return. And we think that he was in Egypt at the time. Of course, those of you from Cornell, I think, know that she was the Queen of Ithaca. Okay, so what were our goals in building a decoder? Well, the main goal for this workshop was to implement a decoder for Model 3, which you've already heard about. But what we really want, the ultimate goal is to really build a flexible decoder, flexible research tool that can be used for advancing the state of the art. Okay? Because Model 3, of course, does not really advance the state of the art. We're just re-implementing things here. So what we'd really like to be able to support is new modeling paradigms. So we want, the ability to use context-sensitive models, such as adaptive language models, like to be able to experiment with sense disambiguation, morphology, and so on. Also, I'd like to be able to support new modeling paradigms. So the models that we're working with here are expressed in terms of the usual source channel framework. We haven't had our ceremonial source channel diagram here yet, but I think it's something interesting to explore to build direct models of the posterior distribution. Okay, and I think one of the reasons that's a good direction to explore is that when you look at the translation probabilities for these models, they're fairly noisy, even when we train on a large amount of data. And I think that's primarily symptomatic of the fact that we're using maximum likelihood training here. But if we build discriminative models and we take into account during the training the English language model, I think we should be able to get much better translation probabilities and possibly better models. And there are other reasons for this. So I'd like the decoder ultimately to be able to support these kinds of models, even that don't use the source channel paradigm. Okay. And also, we'd like to be able to handle new applications. So not just natural language translation per se, But the same sort of modeling techniques and the same sort of decoding techniques can be used for other things, such as summarization and parsing. Okay, so as I mentioned, the decoder is called Weaver, and it's a stack decoder. Now, Fred Jelinek invented the stack decoding paradigm in the context of sequential decoding of convolutional codes many years ago. And it's a very elegant framework for search. It's actually very similar to other types of searching mechanisms, such as A-star search. But I think that the stack decoding formality is a very useful one, a very powerful one, as a way of organizing your search. And what we do is we place the hypotheses that we construct during the search into stacks, where each stack accounts for a unique subset of the French sentence, okay, according to the generative model, right, where the English hypothesis or partial hypothesis is generating the French sentence. Okay. So all of the decoding systems that we used at IBM, at least when I was there, used the stack decoding paradigm. Okay. We have an interface to the CMU Cambridge Language Modeling Toolkit in the decoder. And this is an example, I think, of how flexible software tools can really be beneficial and help jumpstart research projects. So we didn't have to worry at all about the language model here. We just plugged in Roni Rosenfeld's language modeling toolkit, and it works quite nicely. Noah Smith made a nice extension of this that we needed for decoding. I don't know if you're going to talk about that. Okay. So since you're not going to talk about it, I'll just mention that what we needed to do is to hypothesize an English word that would not align with any French word in the source sentence. And that can only be a good idea to include if it's suggested by the language model. So Noah modified the language model to allow us to get those kinds of hypotheses. Now, so when all is said and done, I think that designing a decoder is more of an art than a science in many ways. There are many, many degrees of freedom for designing a decoder. And as I was doing this, there were many details that were unclear. There's only a fairly brief description of this in the IBM patent. And Peter Brown was the one who sort of owned this software at IBM. So during the summer, I was talking to Peter several times, and also the Della Pietras. And Peter just doesn't remember any of the details of the implementation of this decoder. So there are surely many, many differences in what we've implemented and what was used at IBM. I think it would be a great service, actually, if folks at IBM could dust off and make available the old PL8 code that the decoder was written in. Okay, but we have a working decoder, and it was somewhat surprising, actually, to me, how fast it ended up working. So we have a decoder that is able to process fairly long sentences, up to, well, we've worked with it for 30-word sentences. And on a fairly large run, the average decoding time was around 16 seconds, which is quite a difference from the several hours decoding time for 10-word sentences that we were used to at IBM. So partly, this is in large part attributable to Moore's law. But also, again, the decoder is quite different than what we had at IBM. And we're running with very tight thresholds. Okay, so obviously, we can make the thresholds extremely tight and get it as fast as we want. But we're getting reasonable performance here in a reasonable amount of time. But there are many ways that I think this needs to be improved. One point here is that there are unnormalized stack scores. And I suspect that we're making search errors here. Okay. So,
one question.
Yes.
When you say stack, you mean, I assume, what in any other context is called a priority queue?
Yes, that's right. Right. I was going to mention that. So a stack is really a priority queue, actually, it's a pair of priority queues. One for those hypotheses that have been advanced, and then another priority queue for those hypotheses that have not been advanced. Okay, so stack is really a pair of priority queues. And as I mentioned, we have one stack for every subset of the French sentence that we've generated so far. Okay. So there's an exponential number of those, and possible, of course, but we only see a fairly small number. Okay, so in the future development of this decoder, what we'd like to be able to do is to support many different types of models, not just the Model 3 that we've been working with here. And so what we need is an abstract interface to the models that will plug into a fairly general translation system. We need a lot more work on more intelligent pruning and thresholding. And there are many, many other possible speed-ups. Our translation models use binary search for looking up probabilities, and this means that the very common words, which have a very long list of possible translations because they appear often, we're doing maximum likelihood, have very long lists, and the binary search is slow. So this is an obvious way of speeding things up. There are many, many other possibilities. And my opinion on all of this is that this is as much a software engineering problem as it is a statistical modeling problem. I think that in the IBM system, we're as much limited by the actual software that was developed than with the modeling techniques. And I just want to point out that a good chunk of this has been developed together with Adam Berger. So this system has over 10,000 lines of code in it so far, and Adam has written a good chunk of that. So it's as if we've had another very competent graduate student on this project, even though he hasn't been here. And finally, I just want to finish with another quote from Warren Weaver. So Kevin had one of Weaver's quotes on the decoding as cryptography, and I want to briefly mention another from his letter to Norbert Wiener. So as many of you, I'm sure, know, Wiener was probably a natural person for Weaver to ask about translation, because not only was Wiener very interested in the probabilistic mathematical aspects of communication, but he was also a polyglot and very interested in language. But he was also, of course, very eccentric. And my thesis advisor, Ed Nelson, liked to tell the story of how he was at a party and wanted to introduce his wife to Wiener. And Ed Nelson's wife was Chinese. And he went over to introduce her to Wiener, and Wiener said, "Oh, you're Chinese? Do you speak Chinese?" "I do." And he started rattling on in Chinese for several minutes, and nobody got a chance to talk again. So here's another excerpt from that remarkable letter to Wiener way back in 1947. So it says, "One thing I wanted to ask you about is this: the most serious problem for UNESCO and for the constructive and peaceful future of the planet is the problem of translation, as it unavoidably affects the communication between peoples. Huxley has recently told me that they are appalled by the magnitude and importance of the translation problem. So recognizing fully, even though necessarily vaguely, the semantic difficulties because of multiple meanings, etc., I wondered if it were unthinkable to design a computer which would translate. Even if it would translate only scientific material, and even if it did produce an inelegant but intelligible result, it would seem to me worthwhile." So what we have here is a system that certainly does often give unintelligible results and inelegant results. But what I think we have is a framework for advancing the state of the art and developing the next generation of statistical translation systems. So I think it definitely has been worthwhile. Yes.
Is this project ever looked at the problem of trying to find a metric which could be applied to text and tell you whether it would be easy to translate or not? There are people now out there trying to simplify the job of translation by constraining the original writing.
Well, perplexity is I think, a reasonable measure to get an initial grasp, at least, on the complexity of a given subdomain. So in terms of our trigram language models, the perplexity of the Hansard corpus is on the order of 80 or so. But the perplexity of this Czech corpus, for example, is much larger, and that's an indication of the greater generality of the domain, and I think this consequent difficulty of the translation task. So perplexity is useful. There may be other quantitative measures, but
I think the large perplexity of Czech reflects the total inadequacy of the language model. I mean, the trigram language model clearly doesn't work for Czech because it's an inflected language,
right,
and it's free order language, etc. We just have to make we have to make big progress.
But then we can also look at the perplexity of the translation models, as we've done here.
My name is Yasser Alanezan, and I'm going to talk about Giza, or Giza if you wish. I'm not going to talk about the city in Egypt, but it's part of our system, so I'll tell you about it. The way I'll do the presentation, I'll do it in a form of question answering kind of thing. So I'll ask the questions and I'll answer them. And I'll give you a chance to ask more questions if you like. So this is the overall picture of the system, the translation system. So you have two major boxes here. One is the Giza system to the left, which you give the parallel training corpus. And then it produces this translation model that you pass on to Weaver along with the language model. And then you ask Weaver, you bring a new sentence to Weaver and ask it to do a translation, to produce a translation. On the other end, the dotted box to the left is could be done offline, so it's not something you have to do when you are translating. So you could do it offline and then take the translation models and do the translation later. So what is Giza anyway? Well, it's a toolkit for training the IBM-like models, translation models 1 and 2 and 3. That's what we decided to implement, and that's what is in the. So we give it a parallel corpora, for example, English and Czech, and it will produce a bunch of tables. This is what we call the translation model. So you have word translation tables, and this is just given an English word, what is the Czech translation of that particular word. And then distortion tables, which tells you about word movements within the sentence. So it's about positions, English positions of English words, and then how they move into the Czech translation. And then there's the fertility table, which is how many words an English word translates into. And then there's a P0 table, which is just a single entry, which is a scalar of introducing new functional words in the other language. And then there's also the best alignments that the best word alignments that the model is explaining so far. So as the training is an iterative process, so you can look at the word alignments to see how the model is improving its model, its translations. So then why did we develop it? Well, I'm not aware of any documented toolkit that implements the IBM models 1 through 3 that is publicly available and well documented. And most of the implementations stop short of implementing Model 3. And among the different reasons for not doing Model 3, there are two things that I present here. One is it takes more time to implement and more effort to implement. And just by looking at the lines of codes in GISA, this might give you an indication of the amount of effort. So for Model 1 and Model 3 is 10 times more lines of codes of Model 1 and Model 2. And it's also harder to understand from the IBM paper. You know, there's a lot of mathematical formulation for the re-estimation, so it takes more effort to understand. So how to use it? It's simple, or I hope it is simple. Well, so you just type GISA and you give it a specific configuration file and with a set of options, like you know, the English vocabulary file, the Czech vocabulary file, and the parallel training corpus, and the held-out test corpus, and all of these things. And you know, you wait a few minutes, and then you get the model, or the best model. So you get the translation tables. For example, you know, what's the probability given the English word up? What is the probability that you translate it into Czech word nahoro? Then there's the fertilities. What's the probability of translating not into two words, like nipa in French? And then there's the probability of inserting a null. And there's this file for that I was talking about, the best alignments or the Viterbi alignment. And then there's also the perplexity, and this is something you get at the end. So it will tell you how the perplexity is progressing during the training. So what can you customize through the configuration files on the command line? Well, there are many things. Most importantly, you can just choose different training schedules. So you can just tell how many iterations of Model 1 training you want, Model 2, Model 3, and so on. And there's also, you can experiment with different seeding techniques, like, you know, presenting it with initial tables or something, or dictionaries. And there are some people who talk about some of these techniques that we're experimenting with. And there's also how often do you want to write your intermediate files or the model so far. And there's also, you can experiment with different smoothing and cutoff thresholds. Also you can, and this is, you know, controls the output, you know, where to write the files and what to name them and all this kind of stuff. Well, the last thing I have is, why should you use GISA? Well, I claim that it's easy to install, easy to use, and easy to customize. It's hard to develop, or I think so. And it's easy to build on, so, or I hope so. And there's a user-level documentation and online comments for whoever wants to build on it. And it's runs on multiple platforms. At least I tried it on Solaris and Linux and worked. And it's, this is something, you know, presented before, so it's publicly available, and anyone can use it. So, yeah.
What would you say is the ease that you imagine if you were dealing with a language? Well, I'll give you two possibilities. One would be a language that wasn't white space delimited, so take Chinese as an example, and the other would be, say, something like OCR output. In both cases, you could imagine wanting to somehow integrate another model that, for example, produced a lattice. Would you imagine that you have to use something as a preprocessor to pick out the one best and simply plug it into your thing, or is there some easy way to integrate that into the training?
Of having multiple segmentation, you mean? Or?
Yeah, a lattice of some kind, or would you have to choose the one best and then pipe it in?
Well, I would think it's you will choose the n best, because the data I'm expecting is it's already segmented, and you know, corpus preparation is done offline, so it doesn't deal with multiple segmentations and this.
You can build that obviously.
So that was really my question, how easy or hard it would be given, I don't know the detailed paths on
There have been references both to publicly available and to IBM patents. What's the connection?
Oh, I don't know.
We thought I did.
Software's publicly available, the idea, we don't know.
I think it's use at your own risk.
I see, okay.
Let me just say something on this. After we found out that Jim Baker patented Fourier transform, we thought that we should patent something too. So this is completely patented, or this whole thing, I mean, and it always has 15 authors because every one of them would get the same amount of additional money. So anytime somebody met someone in the men's room and mentioned the thing, he became another co-author of the patent.
The question is if the patent's ever been tested.
Oh, sure, certainly not.
What I found out is all these big companies share patents, so we can use IBM patents and Sun's
Yes.
patents and everybody else. So.
Right.
I have a question. Is this, can you do incremental training? I mean, you run a parallel corpus, and you produce a system, and then you come up with another parallel corpus. What do you do?
You can start the training from any model, so and you can give it the initial models, and then it will pick up from there. So I would
what's
imagine
the
that.
contribution of the first corpus?
The initial model.
So the contribution of the first corpus is just as a C. So if you want to use both corpora, you input both of them. Is that right?
Cat the phone.
Okay. All right. Okay.
Any other questions? I'll turn it to Franz.
Okay, I'm talking about, well, it's the wrong starting slide. I'm talking about efficient Model 3 training, about an implementation of IBM Model 4, a simplified version of the IBM Model 4, which does not take into account word classes. And then at the end, after the coffee break, if there will be one, I will present my proposal for follow-up research. And well, efficient Model 3 training, why is this important? It's important because the state of the decoding of the training system in May 1999 was that it took about 100 hours for 50K training sentences. And we plan to make experiments with 1.5 million training sentences without reducing the vocabulary size. Here also was the vocabulary size already reduced, throwing out words which are seen only once. And we wanted to make a lot of experiments with different training schemes, dictionaries, and also to build on top of this new models which require even more complicated training algorithms. And so a lot of work went into making the decoding, the training much faster. This was also joint work done together with Yasa Al-Unaisan. And I think we did a lot of progress. So in May 1999, we started with 100 hours for this 50,000 sentence pairs. And then shortly after the beginning of the workshop, it already took only 8 hours for this, and now we are on 37 minutes, or even a little bit faster, because since August 6th, some improvements. And a very a very straightforward implementation of the IBM 3 model is very slow, because it's not possible, as in the Model 1 or Model 2, to make a mathematical trick to be able to handle all possible alignments. So it's necessary to handle only a subset of alignments, and a straightforward implementation would make it necessary to enumerate all alignments which are considered in training. And this is a very time-consuming and memory-consuming process also. And so a big deal of the speed up was to come up with a trick to avoid the necessity of enumerating all the alignments in Model 3 training. So I want to avoid all the technical details, but it's much faster now. So now to the Model 4 implementation. What are the disadvantages of the IBM Model 3? Why did IBM go to Model 5 and not stopped at Model 3? A big disadvantage is that there are absolute distortion probabilities. So there is a probability which describes the probability of aligning English word I to a French word J if the sentence length of English and French is L and M. And so this does not take into account that words normally move around within phrases, and that an alignment of a specific English word to a French word also should affect the next English word. And the other problem is a deficiency, so that in Model 3 the test perplexity goes up a lot as the model is deficient. But we think the model is in fact much better than Model 2, but it does not show up in test perplexity. And another disadvantage is that it only allows only single word translation and doesn't take into account the word context in the translation model. So all the context information must be brought into by the language model. And so about these two second points, I want to talk after the coffee break. And now I want to talk about the disadvantage of the absolute distortion probabilities, and how Model 4, or the simplified version of Model 4, avoids this. The absolute distortion probabilities are very many. So it's a 4-dimensional table containing for 30 words in a sentence 190,000 parameters. And it also results in sometimes in bad alignments using the absolute distortion probabilities. So this is a Model 3 alignment, where we see that, for example, many is aligned to un nombre, but not this word in between, which should be also, but instead it's taken by criminals. And there are some strange long-ranging alignments which are not, well, this is an alignment of Model 3, and later on I will show the same sentence pair with the Model 4 alignment, which then is better. So in Model 4, this 4-dimensional distortion probability table is replaced by two kinds of probability distributions. One for positioning the first word, which is produced by some English word, and one for positioning the following words, which are produced by the same English word. And I don't want to go too much into these formulas, but the thing is that it depends, the positioning of the French word depends on the alignment of the previous English word to some French word. So it really takes into account if a word is moved from the beginning to the end, that there is afterwards a very high probability that the next word is also moved from the beginning to the end. And yeah. So it's the implementation of the simplified Model 4 is very similar to the implementation of Model 3, the only difference is that it's much more complicated because now more time consuming, as now the alignment positions are not independent from each other but depend on each other. So it's more time consuming, for example, determining the Viterbi alignment of Model 4, or a very good alignment, as it's not possible to determine or there's not known an efficient algorithm for determining the Viterbi alignment. It's very time consuming determining a good alignment according to the Model 4 scoring. And so because of this, it's currently 10 times lower than the IBM 3 training. And well, the results are that now there are much fewer parameters, only 88 parameters versus the 190,000 parameters which describe the distortions. The alignment probabilities are much more focused. Yeah, they are much more focused, and normally I would have a slide for this. Ah, yes, that's it. So this curve here shows the distortion probabilities of Model 3 for position English word 15 and sentence length 29. What are the probabilities that the French word is aligned to position 15, 16, 17, and so on, up to 30. So one can see that it's a quite, it's not very focused. And instead of the corresponding distortion probabilities for Model 4 are very focused, so the highest probability is that if one word was aligned to some word, that the next word is also aligned to the next word. So this is a very high, 50% of the cases, of the alignments are like this. And so this is only one part of the huge four-dimensional Model 3 table. And what you see here for Model 4, these are all the numbers which are in Model 4. All 88 numbers are shown in this. So it's a much more compact representation of the distortions. And also the alignments get better. So this is a sentence I showed before, that now as the Model 4 prefers monotone alignments, now this alignment is right, that criminal is not aligned to this French word. And also some other problem, this long-ranging alignment does not occur. There are still errors, but it's much better. And also test perplexity curves. So this is on Hansard 50K, Model 1, Model 2, and Model 3 then is this perplexity. Starting after 5 iterations, Model 3 with Model 4 reduces the perplexity significantly, and this is directly starting after the first iteration of Model 3 with Model 4. Okay, so I give on to David.
Well, won't you give us a hint about what your trick is that speeds up the Model 3?
Yes. Maybe I forgot. The trick is that, well, maybe then I must describe a little bit more what Model 3 training is. So in Model 3 training, it's not possible to handle all alignments. So one could, or the idea that also is described in the IBM paper, is to determine the Viterbi alignment, and then sum over the neighborhood of this alignment. But even determining the Viterbi alignment, it's not known an efficient algorithm for this. So they start, or good thing is to start with a good alignment. So the best alignment one can find efficiently is Viterbi, the alignment of Model 2, the Viterbi alignment of Model 2. This can be done very efficiently. And then from this alignment, one makes a hill climbing to get the best alignment one can find according to Model 3. And this hill climbing process searches the neighborhood of the current alignment by changing the alignment, moving one alignment link, or by swapping 2 alignment links. And So the thing is that I have a slide also. I don't have one. But it's very important for making this moving and swapping that the calculation of the new alignments could be done incrementally. So it's not necessary to re-evaluate the whole alignment that is considered then, because in this hill climbing process, it's necessary to consider thousands and thousands of alignments. So in the IBM paper, there is mentioned that it's possible to make it incremental simply by dividing the two probabilities, and then there are only some probabilities involved by making the score of move and score of swap. But also, the trick is then for more efficient hill climbing that if one does such a score of move, score of swap, this is nevertheless a costly operation, that most of the scores of move and score of swap don't change. So and the trick is then to store or cache all the costs of such a move and swap in a matrix, and then when a move swap is done, then only some rows and columns of this matrix really change, must be updated, and the other ones remain equal. So it's not necessary to calculate the expensive function score of move and score of swap. And the other trick is in the count collection. Then it's necessary to sum over the neighborhood of the best found alignment. And this normally requires that for every alignment which is in the neighborhood, which are more than 1,000 for a sentence containing more than 25 words, for every of these alignments it's necessary normally to go over all alignment positions. So overall, if the sentence contains 25 words, over 25 positions. And there's also a trick to avoid going over all these 25 positions, so to reduce the complexity by this order of magnitude. And but I think it's too hard for me to explain it now.
I can take a crack at it. So you have a neighborhood of alignments you want to collect the counts over. So you go to each alignment one at a time and collect all the counts. Like in this alignment, this word has fertility 2, and this one has 1. Again, it has 2. But these alignments share so much in common with each other that you don't actually have to visit every one in the alignment, right? Since they share so much, you can sort of visit 2 at the same time and just notice the fact that they're slightly different. And that sort of idea is expanded to the whole neighborhood. So it speeds it up. For me, that was kind of
yeah, the basic point is that so there must be increased always counts for translation probabilities, fertility probabilities. And most of the counts are always added up for the Viterbi alignment, and only some of the counts are for the alignment in the neighborhood. And it's possible that one stores a count for the Viterbi alignment, and some tricky calculations for rows and columns sums allow them to make this in one step and not for every alignment iterative. Additional questions? So, David.
Okay, I'll be speaking first about minimally supervised induction of both morphological analyzers and part-of-speech taggers. One of the impediments that we encounter when trying to apply statistical adaptations in languages is that we actually need, or we can benefit strongly from these taggers and analyzers. Unfortunately, these tend not to be publicly available for virtually any language today. And for example, the Czech analyzers that we used in this summer's project, many person years have gone into developing such analyzers. And last summer we had an entire workshop that was devoted to building Czech parsers using various statistical techniques. And our rather ambitious goal this summer was to have one person spend part-time developing a tagger and morphological analyzer from scratch. And one problem, this person, he didn't speak any French. So we'll see how this worked out. There are a couple of potential starting points here. One is if you are fortunate enough to have supervised training data, for example, triples of inflected form root and some sort of tag, it's a relatively straightforward operation to induce this mapping. And I have some work that was actually originally done at Bell Labs on building trie-based models for representing this mapping in a compact manner and also applying it readily to unseen data. The interesting problem actually arises in the context of unsupervised or minimally supervised techniques for this. And there's two sort of natural starting points. The first one is to begin with a small inventory of suffixes and stem changes. For example, you might start with a small list of the affixes of French, a list of some observed or valid stem changes, and then basically some just raw word lists. And using EM-based iterative learning, we come up with alignments between certain French forms and a triple, sort of root form, a stem change, and then a direct affixation. Another paradigm to take this here is to start with strictly unaligned inflected root word lists. So we have, for example, a list of infinitive verbs and a list of inflected verbs. And then the question is, without any inventories of affixes or stem changes, trying to induce those. And the key concept here is starting with the longest strings, the longest string matches. So here we observe that the probability, since there's only two or a few words that share this very, very long common prefix, we can induce a certain or infer a certain morphological relationship. We first learn the affixes from direct affixation, where the affix is the only difference, and then to sort of fill out the mapping table, we can incrementally add increasingly more complex spelling changes. We start off with single letter spelling changes and increase to potentially multiple letter changes. Now, there's some problems with these approaches. One, if we have missing roots, we don't have a natural way of sort of finding the appropriate correspondence from the inflected form to the root. We might go out of our way to find a more complex stem change that actually takes us to the wrong position because the root we were looking for wasn't there. So one solution to this is to try to find a larger training corpus. Again, this is a raw corpus, not tagged in any way, or some sort of reference dictionary. But I would like to point out that the techniques that we've used this summer are actually robust enough to provide best guess analyses if there's no root present. A more significant problem has to do with sort of spelling errors in the root lists. We find, for example, that if you have the bad fortune of having concurrencer with a sedia in your root list, that has a much higher probability as an overall analysis because the null goes to null stem change is overwhelmingly preferred if present. The affix has the same probability. So in general, if, for example, what would appear to be a regular stem with no stem change is present, that typically is preferred over a more complex but correct analysis. Now, one way that we looked into solving this problem is attempting to model the probability of the root so that these erroneous stems are deprecated in some way. And what we actually really want to do is have the probability of root be conditioned on the word class, so probability of a certain root given that you're talking about verbs as opposed to nouns, and then also dynamically probability of this particular word class given a particular context and maximize over all instances of a word when doing this classification. So this brings us to a technique which I'm quite excited about today and have been recently, called code training. Actually, I started using this technique back in 1995 with a sort of minimally supervised learning algorithm for word sense disambiguation, and it turns out that what I was doing was actually an instance of this general technique of code training that was discussed by Bloom and Mitchell in '98 and Collins and Singer for named entity recognition this year. And the general concept in very simple form is that you have two sort of roughly orthogonal models. A part-of-speech model that predicts the probability of a tag given a context, and a affix model that predicts the probability of a tag given some sort of prefix, suffix model. And we have good reason to believe that these are roughly orthogonal information sources. And if we, ignoring for a second where we begin here, let's say you're given a small set of nouns and verbs and representatives of different classes, you can start by training a rough context model for these things that would distinguish them based on trigrams and context. This provides, then you can reapply that data to new contexts, which gives you a rough distribution over classes for new words, and hence by sort of taking cases where there's a very, very strong likelihood of a particular class for a certain word summed over the corpus, we now have introduced a enhanced set of potential candidates for training our affix models, or at least in the first round, our first set of candidates. From that candidate list, we can then train these ending models to predict part of speech given affix, which we then apply back again to the corpus to give new or better analyses of words which help us build our context models. And then this sort of cycles into a convergence. Now, there's some interesting issues that were raised in the paper with, that I had with Silvio Gutierrez this summer at EMNLP in terms of do you do sort of straight EM-based, even if something has even slight probability that is introduced to this model, training model with that small probability, or do you have some sort of thresholding where things are completely kept out of the code train model until they reach a certain threshold, and then they participate in a weighted fashion. There's really no time to discuss that in detail. Some example analyses that actually learn by this system, again, starting roughly from scratch, it is a nice set of irregular stem changes, nice set of affixes. It was kind of satisfying to see this come out. Evaluation was difficult, partly because we had no training data. We have absolutely no correct morphologically analyzed data for French. If we did, we wouldn't be doing this here. And I don't speak French, so I can't really eyeball the data very well. But based on sort of rough analysis, it appears that fully supervised methods get in the mid-90s. Again, this is on a primarily on a verb-weighted task, which is harder than the nouns. If we look at using only this affix and stem change inventory and no special corpus requirements, you get 96.2%. If we start with only the unaligned part-of-speech tagged root word list and inflected word list, so we have just the infinitive verbs and just the inflected verbs. And this is, again, crucially depends upon these being fairly accurate. We can get 97.3%, and if we start with both, so we have an inventory, a small one, we're talking about something on the order of maybe 15, 20 initial stem changes and maybe, I think, 40 affixes for French. If we start with that, and then a fairly robust list of inflected forms and root forms, we actually get very close to the fully supervised score. A couple bits of future work. One is we were very interested in attempting to model this stem change probability conditioned on more linguistically sound principles rather than allowing any unrestricted change, which tends to converge upon some pretty bizarre analyses. Having things that are either phonologically similar or based on systematic processes such as gemination or elision that are observed across many languages. So we have some constraints on that set of morphological processes. Another task that we're looking at is trying to borrow inventories and probabilities from related languages. So if you have a tiger for Spanish, you can sort of bootstrap the inventories and spelling and stem changes, at least from some level, on that language. We're going to other Romance languages. Also, we're looking at I'm looking at the task of if you have a set of processes such as reduplication or vowel harmony or whatever, trying to model these as being consistent across members of a language family. A very important goal in the next week or so is to try and finish up a full evaluation of how these sort of models help in full decoded translation. We'll have some results on the check later. And also I'm very interested in minimally supervised noun phrase bracketing based on and helping to do model alignments. So if, for example, we induce or from the align corpora that in the English determiner, in French determiner noun adjective tends to align with determiner adjective noun. In the English side, we can attempt to do what Jan will describe as sort of this check prime transformation to get things closer to the original form. Also, there's this hypothesis that the bracketing, noun phrase bracketing is somewhat impermeable for alignments, and we typically don't want to get alignments that cross these things. So if we have an initial bracketing of English, for example, that can help constrain the potential alignment options. Again, this is all sort of ongoing work that we're going to include in the final report for the workshop. The second thing I'll be discussing now is a rather exciting, to see if it worked actually, exciting effort in machine translation in one day. We were brainstorming in our first planning meeting about ways we could sort of show off the system, and there was a suggestion that, wouldn't it be great if we could just take a new language off the shelf and to apply the techniques in just one day, one person day, one day per team member, and see what we get. And we were very audacious and decided to pick a language that was extremely hard, like Chinese and English. So this is certainly not at all trivial. And the miracle is, in literally one day, it worked. We in 24 person hours, basically I started around, I think, midnight, and by that afternoon, Kevin was checking out real translations and alignments for Chinese, which is really exciting to see happen. I'll show you in a second, but briefly in terms of the details, we started with parallel Chinese English corpus from the LDC, the Hong Kong laws corpus, 240,000 sentence pairs. What's nice about this is it's publicly available. Anyone can get it off the web. We'll be distributing it here with our alignments and various tables as a sort of resource to the community. We I obtained various online dictionaries in this 24-hour period, mind you, from various sources. There's one that's more or less publicly available. CE Dict, 23,000 entries available on the web. We'll give the URL for that. And Professor Su at Behavior Designs Corporation in Taiwan was also kind enough to give us a fairly large dictionary, which is also available for nonprofit use. And we actually didn't use any in the two alignment results that I'm going to show you, but we plan to do so. Also, segmentation programs, the major sort of experiments we ran, we're looking at different segmentation techniques. One option was based on a simple character level segmenter, which again I wrote in the 24-hour period. And the second one was based on something that was borrowed from Professor Su's lab, which gives more robust word segmentations. Now, the issue here has to do with a sort of the character of the alignment outcome. In character-based alignments, you get nice behavior, such as Hong going to a single character and Kong going to another one. Sorry for my Chinese sounds are not working very well today in LaTeX. And things like government will actually go to two characters, which is all well and good and proper under the Model 3 approach. word-based alignments, once we actually sort of chunk these things together, we actually have sort of fixed the government problem. We have the more desirable one-to-one mapping, but we find that Hong Kong, because of peculiarities of Model 3, Kong goes to that compound, while Hong goes to nothing. And this is obviously going to be fixed in Model 4s and above, but it's something that certainly, this is the character of this. I'll show you in a second how that is. Alignments, this is based on the character model, where it's, again, every single Chinese character is its own token, is remarkably good. We've discovered that before July 1997 actually maps very robustly to the beginning of the sentence, and for the most part, these are all more or less correct. Again, this is based strictly on no knowledge of segmentation at all. You just want one character per token. There's some interesting behavior. July, for example, actually maps to the characters for 7, month, and then the day symbol. So although the day symbol technically goes with the day number, it's interestingly that because it's so typically occurs with the month compounding, it actually gets aligned with the month itself, and one is aligned separately to its own token. And so that's satisfying. Here's very quickly the output of the Weaver decoder on an actual Chinese sentence taken from my screen. That period shall be deemed to extend to and expire on the day after that second sitting. That was the correct translation. It's amazing how circumlocuted this text is. It's really quite painful to read at times. The character-based model got then the period for which shall be treated as extend the second occasion, counsel may circular and the date of expiry. Now counsel is one of these sort of spurious things that was inserted because it happened to match to one side of a compound character. And this is one of the dangers of the character-based model, is that you get these random words sort of thrown in there from the fact that there's non-compositional compounding. You have two words, two characters that together make a real word, but when they're separate, they have completely unrelated meanings, causing this kind of thing to show up. But it's more or less has the basic information. The word-based model is a little bit better. Again, this is a randomly selected sentence. There's something fancy about this selection. Then that period shall be deemed to extend the second sitting and the date of expiry. Now, there's a preposition missing here, but it's not disastrous. Again, this is one day. We can't. It's certainly much better than what I could do if I looked at that on its own. Now, to finish up, it wasn't only Chinese that we looked at. We actually have a sort of ongoing experiment with Dr. Takehiro Utsuro from Nara Institute of Science and Technology, who's visiting Hopkins this year. We're trying to get a Japanese-English system running under the same sort of Egypt paradigm. The alignments are almost finished, and Utsuro has been working very hard with me on sort of some of these normalization issues. One of the most challenging one is handling the sort of major word order divergences you find in Japanese English. The verb, as you know, goes to the end, and you get major sort of constituent level reordering. So what Jan will discuss in a second, this notion of Czech prime or Japanese prime is very important in that you want to reorder the things at constituent level to be as close as possible to the desirable English-like word order. Now, there's nothing imperialistic about having everything sort of mapped into standard English syntax. It's just you have much better distortion and fertility models if you do so. And you can pretty much treat this as a new language, the Japlish, if you want to call it that. Another issue that's sort of challenging here is inserting tokens for null and after. There are a lot of, for example, subjects are often elided in Japanese. And one technique is simply to, every time you're missing a subject, simply to insert a token in the Japanese, which will most likely align with it, he or she, with decreasing probability. And in the ideal world, we would actually have an afro trace that would actually have different tokens based on the most likely co-referent. And also, we're very much interested in inducing this dependency-based reordering from data, as opposed to routing actual case-based rules to do it. So there's some interesting, exciting work going on here as well, and maybe by the end of the next month, we'll have 4 languages in 6+ weeks. Yes.
Last question. After the successful of Model 4, and then we stopped seeing slides that said publicly available and freely distributable. Is any of this stuff making it into the toolkit?
All of the Chinese, 100% of it is going to be distributed. The French analysis will also be a complete table of verbs, the part-of-speech tagger. That's all going to be in there. So it's available. Plus, the Hansards are also available and publicly distributable, as long as we don't offend the dignity of the Canadian Parliament.
Do you have some translation statistics between English and Japanese?
Not yet, no. We hope to have some in the near future. We're just waiting for the alignments. The parameters are not quite the same as other languages in terms of inducing this, so it's a challenging task.
For Chinese translation, was the parallel corpora pre-aligned sentence by sentence, or just they were?
It was pre-aligned using the Gale-Church algorithm, which is actually much. I mean, Dan's similar techniques are much superior to that. So, if we ran Dan's code, we would actually expect to get better initial alignments.
Good afternoon, my name is Jan Surin, and as a Czech member of MT team, I would like to say something about the experiment on Czech-English translation. So let's start with resources. We have this Czech-English parallel corpora from Reader's Digest. There are short fiction articles translated from English to Czech. There are these numbers of articles. It's actually 450 articles and 53,000 sentence pairs, which were aligned automatically, but we need to realign them by Dan's tool during the workshop because the previous alignment wasn't sufficient enough for our purposes. And there's about 1 million words in each language. We have also morphological analyzer, part-of-speech tagger, and lemmatizer from Charles University of Prague available, and also the statistical parser for Czech from previous NLP workshop here in Baltimore. We have also Czech-English dictionary available for our purposes. I would like to say at first something about Czech language. So Czech is high inflection language. There are, for example, 14 forms for each noun or personal pronoun. For comparison, there is something from information from corpus that we have 72,000 word forms in Czech against only 31,000 forms in English. Next to the Czech is prodrop language. That means that the subject pronoun like he, I, they has a 0 form, and there are no articles in Czech before nouns, and also English prepositions equivalents can be sometimes the part of Czech noun or pronoun inflection. And we can find some information also from that know that there is 15 more words in English than in Czech in our corpus, and more Czech is a free word order language, which what is really a problem in these models.
You see any so-called word model in Czech, for example, for Japanese or Korean, they are called pure languages, but there's a strict constraint that verb should always come at the end, although in principle they can unmute it. Also, the canonical word order is subject, object, or something. So do you have some?
Okay, you can order Czech sentence in this canonical word order, but and we can say that it's usually in this form, in this order, but this like syntactic function is included in inflection, so it is not, we don't need to have this
The
order.
reason I'm asking you this question is that if there's one single canonical model which keeps occurring over and over again, it will make the mapping much simpler than, let's say, having all different six words, let's say, six different words occur like many different times. Do you understand? So like if there is a canonical word order which occurs 90% of the time as opposed to, even discrete about 20% or 30%. So the mapping might be much easier, I mean, intuitively, that, because there's a certain default word which is recurring as opposed to having three words occurring on.
Okay, I think if Fred can be. Well,
I understand what you're saying. I don't know. So I'm just not a linguist. I'm just a native speaker of Czech. First of all, if you take sentences which have only one clause, it is literally true that any order makes sense, and it does not. In fact, it essentially means the same thing, but different orders are answers to different questions.
So the emphasis is different.
The emphasis is different, but as far as canonical order, I don't know. I mean, maybe 70% of it wouldn't be 90%. That's for sure. It might be 70. Yes, I mean there will be something that's more frequent, but you can, for emphasis or to show how creative you are or clever or whatever, you can turn it around, and
Yeah. I think for this corpus I can say that there is translation from English to Czech, so it's maybe influence of this translation also that the Czech as a result have something like more English order or something like that. So what I want to present here is some pre-processing of Czech into English-like Czech. Say it's because our model, which we have available now, allows only alignment one-to-many from English to Czech. So it's useful to have more words in Czech than in English in this case. But the real situation is opposite. So we are adding some new words into Czech input, and we hope that the performance of translation will decrease by this. So here is an example of Czech parse sentence. It's dependency-based parsing. So we can see there are glosses. The first item here in belonging to each node is English gloss. So this sentence says something like, I am convinced that the teamwork is the key for the realization of one's dreams. And you can see that in English there is significantly more words than in Czech. The sentence in Czech includes these bracketed words, which are the artificial words, which we want to add it into Czech input to improve the translation. So I can move it. So you can see that it's 1, 2, 3, 4, 5, 6 more words. There is, for example, this artificial I, which is instead of missing subject in Czech here, and there are articles, and at the end we can see artificial preposition of, which is in case of Czech genitive. So now about Czech prime. It's English-like, and we call it Czech prime. So we are at first transforming the whole corpus into lemmatized version of this. So what does it mean, lemma? Lemma is the basic form for each word form. So for example, for noun, it's nominative singular. For verbs, it's infinitive or finite version. So we are transforming into lemmas and adding these artificial words into lemmatized Czech. we are also adding some information about singular and plural to nouns, which was discarded by lemmatization. And we also adding this missing preposition if there is no in Czech. Sometimes it is here, so only if there is missing preposition we are adding this, and we are adding this missing subject if there are no of them. And we also explored the syntactic reordering of Czech, but we didn't implement it because I think it's a goal for a workshop, whole workshop or something like that. So. Yeah, I think it's possible to overgenerate this insertion, but we hope that the model can resolve this situation. So here are some examples from training corpus, how it's aligned in training corpus, these artificial words. We can see this artificial, the percentage here. What does it mean? It's mean if we have in how many cases the artificial word is aligned to sufficient English word. So here we can see the with singular is aligned to indefinite and indefinite article, and artificial word the for plural is only on the first fourth position. There is only the in situation. There is some preposition, it's aligned off, it's nice, I think. And there are also very high probability that, or maybe it's not probability, just counting how much, in how many cases it happened. So subject for first singular is aligned to I, and subject for third person singular is subject to he, and there are also artificial word for negative verb, because this is part of verb in Czech. So there are these and, not, and no. I think it's significant. So now I have here output from, or screenshot from Cairo. I have also it on computer, but I think we are out of time, so I just try to use this slide. So in the first column there is a gloss for each word, original Czech. In original Czech sentence there are some part of speech text. I just make it more readable like this. There is a Czech sentence. The crosses are in the position where I add the artificial words. And here are this English translation. It's a real translation from our system. You can see how, if it's good enough or not. And here there is a reference translation in the corpus, in the last column. So you can see that sometimes these hypotheses or artificial words found the corresponding word in English, sometimes not, but it's, of course, up to training to find
What
this.
is the first column?
First column is for artificial word before následující. That's like that is, look at gloss. It's something like singular the. I didn't add the lemmas here, but
for instance, what is this? What is the word current? What does the word current have to do with novi?
Sorry, that's the first translation from our lexicon. So
from your lexicon, novi
maybe,
and rock translates as career.
Maybe.
That can be.
Ish again, but yeah. Backward aggression.
The online checking, the stationery that we got.
But yeah, I just generated
This doesn't help the reader. It's not expected to be a translation.
How can it help the reader? I mean, what he's got there is rock is year, and it is helpful to translate year as career. Is that what you feel is helpful?
Current and new are reasonable
maybe there were more words in the dictionary or something like this.
Recreational is translated as backward. I mean, you like that?
Okay. I will change this. but we need some translation system to translate. That's a dictionary. So okay. But you can see this is the real translation from our system. And
So in principle, that left column might possibly be better to have a pull down for each one to show you all the dictionary translations.
Yeah, it's possible.
This is just showing you the first one in the dictionary or some other thing.
Yeah, I just choose the first one dictionary.
It's a crazy dictionary, all right? It's not the first one in some
It's generated from one of the translation system, this dictionary. So okay. So next, something about evaluation. We want to know how good is this idea to change input of check or check input. So we made a human evaluation on this. It was just close to this time, so it's and I must say that it's only for our internal purposes. So don't ask so much about this thing. So this evaluation has been made by 2 evaluators, and it has been made distantly by Yasser tools, which is in Netscape or HTML format, so it's possible to make it distantly. And there are 5 marks assigned to each translation. From 1 to 5, 1 is the best, 5 is the worst. It's like in school in Czech, I don't know. And so we have 2 evaluators and 66 randomly chosen sentences from testing data. And here are the results. The numbers in columns are the average number of assigned mark corresponding to each column. At the beginning, you can see these marks. So, and in the last column, there is average of marks assigned to each commercial or to each translation system. We see here I hope you can see the improvement of from our baseline system to first lemmatized version. There were no artificial subjects or something like this, and here is a result for Czech prime. This is output from Weaver, and it's based on GISA tables. So we are now closer to commercial system, but we didn't beat them, so maybe next time. So there are 2 Czech commercial systems, so its names are PC Translator and Skix version 4.2.4.0. I think you don't.
So I just want to understand the evaluation method. You asked the human evaluators to give goodness rating on a scale from 1 to 5?
Yeah, it's something
what
specifically
did you ask them?
Yeah, it's difficult. Maybe it's just to scale translation. You can say, I just ask to make a relative order of translations.
Of order? So you present
No, exactly. No, just say that add mark 1 to the best, the really good translation.
Okay,
yeah, and
good translation. You
okay.
can say things like accurate versus fluent versus. I mean,
yeah, good translation. Yeah,
scale from 1 to 5.
And 5 to worst translation, and then have some influence of the system, which